So our next speaker is addressing a big topic, which is big data. Big data is very popular these days, and I'm pleased to introduce Harry Zoot, who is going to be talking about that.
Okay. Well, I was particularly impressed by how fancy the slides were from the previous speakers. Even if I'm the youngest, probably newest faculty member in the School of ICS, I would use the most old-fashioned slides. So I'm doing research on program analysis, programming languages, in general programming languages, software engineering, particularly program analysis, runtime systems, memory management. I gave a talk in this forum last year, actually, talking about this problem called memory bloat. If you were here last year, you know the type of research that I'm doing. So today I'm going to talk about, I'm not going to cover too many things. I'm going to focus on one particular piece of my research, which is the development of highly efficient big data applications using object-oriented languages. So modern computing has entered the era of big data, as everyone here knows. So we have so many different large-scale data-intensive applications in the world, and there are actually a lot of services that we use every day, like credit card fraud detection, for example, web search, or the stuff that Andrew talked about in the beginning, are all powered by underlying big data applications. Those big data applications need to extract useful information from a sea of data items, very large, massive amount of data that cannot possibly fit into the physical memory of any possible machine in the world, probably. So being able to provide fast service to a lot of different concurrent users requires the underlying big data applications to be highly efficient, highly scalable, and highly responsive. However, we found that most existing big data applications written in object-oriented languages cannot achieve this goal because of the performance reasons. So typically, if you look at existing big data applications, you found, roughly speaking, we can classify three categories of applications. We have data flow frameworks such as Hadoop, Hierarchs, Spark, and Storm, in which data manipulating algorithms are represented by pipeline operators. And those operators are combined into pipelines. And then eventually the pipelines are executed to process a stream of data. And the second category of applications is a message passing system such as Giraph and Parallel, in which different nodes in the graph communicate with each other to pass messages. So in those systems, programmers have to think as vertices. So the programming philosophy for those systems is thinking as vertices. So you basically have to think as vertex in order to communicate with neighbor vertices to exchange information. And eventually, the third category is high-level languages such as Pig, Hive, Asterisk DB, Flam Java. Those languages are typically built on top of the previous two categories of big data applications in order to allow developers describe data manipulating functions in a more abstract level. So for example, you can use Pig or you can use Hive to describe a certain kind of data that you want to process in a more abstract level, at a more abstract level. So big data comes with big challenges, of course. We found that all of those applications that we talked about in the previous slide, except for Spark, are written in Java, of course, because Java is easy to use and has large community support. Spark is written in Scala, which is a functional language. However, it relies on JVM to execute, which means that it suffers from all the inefficiencies that the JVM has. And we found huge performance scalability problems. Actually, we did a study on a very comprehensive study on the performance of various popular big data applications. And then we have this paper to be published in this ICMM, International Symposium on Memory Management, coming up next month. So we actually studied the performance of those different applications in terms of their scalability and responsiveness. So we found a lot of different performance problems. This slide gives you a few examples. For example, the first thing that we did is we implemented this algorithm called PageRank. PageRank is a very popular page analysis or page ranking algorithm used widely in those search engines. If you go to Google, if you search any website in Google or search anything in Google, and then you will see a list of ranked web pages as a result. So the ranking algorithm is actually this PageRank thing. So we implemented PageRank on 3 popular frameworks: Giraph, Spark, and Magnified. And we found that, unfortunately, all those implementations failed to process 500 megabytes data on a 10 gig heap. So you cannot accept it. The input set is 500 megabytes data. You have a 10 gig heap. You cannot process it. So there are a lot of inefficiencies and redundancies in the implementations of those frameworks. As a second example, if you go to those websites, for example, those programming websites like stackoverflow.com or various mailing lists of big data applications, you will see a lot of different complaints from developers on poor performance and scalability, especially the complaints on excessive object creation as well as high garbage collection costs. You will see a lot of complaints like this. And then the final experiment that we did was we implemented a simple SQL query that groups data from different database tables. Okay, so we implemented this query that is very simple using a hash table data structure, Java hash table data structure, and then we found that 47% of the execution time was actually taken by garbage collection, which is again unacceptable for production systems. So because you use the Java hash table to implement this grouping, and the hash table maintains a lot of references to different objects that contain in the hash table, so the garbage collection has to traverse each of those different references in order to see whether those objects are still reachable. So that's the reason why we have this huge GC cost over there. So if you want to know more information, sort of details of the information, you can read this paper. So what is happening there? The question I'm asking, I guess most of you guys are asking, what is happening there? What is exactly the performance bottleneck that prevents those applications from reaching their performance goals? So we found excessive object creation in the root of all evils. If you're a big fan of objects, don't get pissed off because I'm saying this only for big data applications. So each object has a header in JVM, right? Each object has a header, which contributes to space overhead. And each object is subject to GC traversal, which contributes to both space and time overhead. And usually what happens in the Java world is that a Java program makes heavy use of object-oriented data structures with many layers of delegation. Those delegations are typically implemented by pointers, right, to connect different objects. So the pointers also contribute to space overhead. So we have a lot of different overheads from different parts of the implementation of the object orientation. Even more seriously, the culture of object orientation encourages developers to create objects for all different tasks. Even though in many cases those tasks are extremely simple. You just create objects to achieve modularity, for example, to achieve improved readability, maintainability, different good properties, high-level properties. However, they take it for granted that all those different things are free. What happens is that they're not free for a lot of those large-scale applications. So this picture shows a runtime structure of a vertex, object-oriented version of a vertex in the implementation of PageRank algorithm. Okay, so remember that we have this message passing system in which all different nodes are represented by vertices, right? We have a huge graph with thousands of vertices. Each vertex represents maybe a server or something. And then this picture basically shows the object-oriented representation of a vertex. So each vertex has a unique ID, and the vertex has a list of incoming edges, and vertex has a list of outgoing edges, and also vertex has a list of messages it wants to send to its neighbors, right? So if you look at a typical runtime representation or runtime structure of a vertex, you will see a structure like this in the heap. Okay, and then we did some simple math to calculate the overhead of this representation. We found that the space overhead of the vertex is 16 times m plus n plus 148. So where m and n represent the number of outgoing edges and incoming edges. So you basically have this as the space overhead, while the actual data needs only this, 8 times m plus n plus 100 plus 24. So basically the overhead, the space overhead of this representation is even larger than 2 times of the size of the actual data. So the overhead is more than 2 times. And then this representation contributes to larger GC costs because the Java hash table, if you use the Java hash table to represent things like this, the Java hash table can contain millions of objects in a typical big data application, and the GC, the garbage collection, will traverse each reference to do this reachability test. So that contributes a lot of runtime overhead. So it's huge. So the effect of large number of objects may not be significant for regular object-oriented applications. If you write regular Java applications, you probably wouldn't see as much overhead as this, because first of all, we have optimizing compilers in the Java, in regular Java. We have a garbage collection algorithm in Java that can all remove the runtime penalty for you. So for example, object-oriented, optimizing compiler Java do a lot of stack allocation. Even though you create a lot of objects, it might be able to remove the penalty by doing stack allocation, by performing escape analysis. However, this wouldn't happen here in the object-oriented world because a lot of those objects can go very far away, so can flow to methods that are far away from their creating methods. And then a lot of those objects are temporary objects. So that's the reason why typical garbage collection algorithms wouldn't work well for those cases. So now you may ask me questions. Why not switch back to an unmanaged language like C++? It appears that Java is not the right choice for implementing those big data systems level applications. So what we found is that a typical big data application often exhibits clear separation between control paths and data paths. So what is control path? What is data path? So a control path is actually, so if you look at this pipeline system, the control path is a part of the program that controls the execution flow, that moves data from one operator in the pipeline to the other operator. It controls the execution flow of the data. It never touches the actual data. It never represents the actual data. On the contrary, the data path represents and manipulates data. For example, typical data path components include hash functions, group functions, comparison functions. Those different functions actually need to access the raw data and represent those raw data, right? But if you look at the development cost, development effort for the control path and the data path, you will find that the control path takes, well, if we did the study actually on 6 big data applications, the study shows that the control path takes on average 64% of the lines of code in the control path, in the whole, across the 6 applications. And the data path takes only 36%, but creates more than 90% of the runtime objects. Only 5 minutes? Okay. So, well, the 36% is even an over-approximation of the development effort because a lot of those data manipulating functions can be reused across different applications. So the question, or the challenge we want to face, we want to solve, we want to overcome, is that can we enjoy both the benefit of manager language for control paths and the high performance simultaneously for data paths? Can we achieve this goal? We perform, so first of all, our proposal has 2 components. So the first component is a buffer-based memory management system. So the key idea is that we want to design a bloat-free data path. Because control path is harmless. You can create objects, do whatever you want, because control path would not create a lot of objects anyways. So data path is the thing that we want to pay special attention to, right? So key to designing a scalable data path is to bound the number of objects. So in other words, the number of objects cannot grow proportionally with the size of the input data. Because the input data can have a huge number of data items. You cannot possibly to represent those data items using objects while simultaneously achieve scalability. So what we propose is that we allocate data items in buffers, which themselves are Java objects. Okay, so you immediately reduce the number of objects in the system from the total number of data items that need to be processed to the number of buffers, and you can easily control the number of buffers to a very small number. Okay, and then data items in buffer have similar lifetimes and can be discarded altogether at the end of the iteration in which they are processed. So which really make the memory management task really easy. And in order to access data in the buffers, we propose this accessor-based programming model. So remember now that all data are in buffers, so are in raw buffers actually, the bytes. So we need to come up with this new programming model to access data from those buffers. So how are we going to do that? We use this accessor-based programming model. An accessor can bind itself to different data items. So basically, for each type of data item, we create a type of accessor. And then we use accessors to access different data items of the same type. And then for each type of data structure, we form an accessor data structure in which each accessor accesses a data item. At the runtime, so basically, this picture shows the structure of an accessor, the accessor structure actually for the vertex representation. So now all the vertex data is in the buffer, right? So what we do is that we form a structure like this, which has pretty much the same skeleton with the original vertex data structure, and then we push the data, the raw data from the buffer, to flow through this accessor structure, so that each accessor on the structure can bind itself to a subregion of the data in this buffer. So each accessor here binds itself to a subregion, and then eventually we use those different accessors to process the different subregions of data that is inside the buffer. So we did an initial evaluation, and the evaluation results shows that the below-free version scales well with the size of the data set. So this picture shows the scalability. You can easily see that when we increase the size of the data set, the scalability works very well. On the other side, all the object-based implementations run out of memory as a 10 giga scale. Okay. This is the first stage of the proposal. So actually, we're planning for a three-stage, long-term three-stage research plan. The first stage is the below-free design methodology, so which contains these two different techniques: a buffer-based memory management technique and the below-free programming model. And the second stage is to provide a compiler support that can hopefully automatically transform a regular Java program into a program under this below-free design, because you have different worlds there, object-oriented world and object-free world. So the goal of the second stage is actually to build this bridge between the two worlds. Okay, and then in the third stage, the goal is to provide a maintenance support, because apparently, if you want developers to implement programs, these below-free programs that introduce a lot of overhead in the maintenance, debugging, testing. So we want to use the third stage to overcome those challenges. So the current status, we're right now between stage 1 and stage 2. And this is a joint work with the database we prepared UCI, particularly Van and Walker, Boo, and Mike Carey. Thank you very much.